Dear friends, today was the 50th anniversary of the launch of satellite Aryabhata, which was a milestone in the history of science and technology in our country. And today we have with us Sri N.S. Chandrasekhar, who as a young engineer took part in the integration process of the satellite. And we have a few more persons who were associated with the ESRO. In today's program, Sri P.M. Siddharthan, who happens to be an editorial board member of LUCA, the online science portal of Kerala Shastra Sahitya Parishad, and who also was a scientist working in ISRO. He will chair the session and introduce the speaker. Over to you, Siddharthan, sir.
Okay. Thank you, Dr. Shaji. I briefly introduce Sri N.S. Chandrasekhar. I'll do it in Malayalam first because most of the audience will be from Kerala. I'll follow it up with a brief English introduction also. Mr. N.S. Chandrasekhar, Aryabhata project മുതൽ ആര്യഭട്ട ഭാസ്കര 1, 2 and ആപ്പിൾ പ്രോജക്റ്റുകളുടെ സിസ്റ്റംസ് എഞ്ചിനീയർ ആയിരുന്നു. സിസ്റ്റം ഇന്റഗ്രേഷൻ ആണ് മിസ്റ്റർ ചന്ദ്രശേഖറിന്റെ പ്രധാന പ്രവർത്തന മേഖല. അദ്ദേഹം ഒരു EMI, EMC സ്പെഷ്യലിസ്റ്റ് കൂടിയാണ്. സ്പേസ് ക്രാഫ്റ്റ് ഇന്റഗ്രേഷൻ, ടെസ്റ്റിംഗ് ആൻഡ് ലോഞ്ച് ഓപ്പറേഷനിൽ ഹെൽപ്പ് ചെയ്യുക തുടങ്ങി ആര്യഭട്ട, ഭാസ്കര, ആപ്പിൾ, IRS സാറ്റലൈറ്റുകളുടെ പ്രവർത്തനത്തിലാണ് ഡോക്ടർ ചന്ദ്രശേഖർ ഇൻവോൾവ് ചെയ്തിരുന്നത്. ഡോക്ടർ ചന്ദ്രശേഖറിന് 1977 വെർട്ടിക്കൽ ഡൈനാമിക് ബാലൻസിംഗ് മെഷീൻ എന്ന നൂതനമായ ഒരു വിദ്യക്ക് ഇന്ത്യൻ ഇൻവെൻഷൻ അവാർഡ് ലഭിച്ചിട്ടുണ്ട്. അതുകൂടാതെ ഡിസ്റ്റിംഗ്വിഷ് അച്ചീവ്മെന്റ് അവാർഡ് കൂടി അദ്ദേഹത്തിന് ലഭിച്ചിട്ടുണ്ട്. ഇസ്രോയിൽ നിന്നും റിട്ടയർ ചെയ്ത ശേഷം അദ്ദേഹം പല വിദേശ ഇന്ത്യൻ കമ്പനികളിലും പ്രവർത്തിച്ചിട്ടുണ്ട്. അതിൽ ഞാൻ ജസ്റ്റ് 2 എണ്ണം മാത്രം ഇവിടെ മെൻഷൻ ചെയ്യാം. ധാരാളം കമ്പനികളുണ്ട്. അപ്പോളോ കമ്പ്യൂട്ടിംഗ് ലാബറട്ടറീസിലും ഗ്രീൻടെക്സ് കമ്മ്യൂണിക്കേഷൻസ് ലിമിറ്റഡിലും അദ്ദേഹം പ്രവർത്തിച്ചിട്ടുണ്ട്. എനിക്ക് വളരെ സന്തോഷമുള്ളൊരു കാര്യമാണ്, ഞാൻ ഇസ്രോയിൽ ചേരുന്നതിന് വളരെ കാലം മുമ്പ് തന്നെ ഇന്ത്യയുടെ ബഹിരാകാശ രംഗത്ത് പ്രവർത്തിക്കുകയും നമ്മുടെ ആദ്യത്തെ ഉപഗ്രഹമായ ആര്യഭട്ടക്ക് വളരെ വലിയ സംഭാവനകൾ നൽകുകയും ചെയ്ത ശ്രീ N.S. ചന്ദ്രശേഖരനെ പരിചയപ്പെടുത്താൻ ലൂക്ക എന്നെ ചുമതലപ്പെടുത്തിയത് ഞാൻ വളരെ സന്തോഷത്തോടുകൂടി സ്വീകരിച്ചിരിക്കുന്നു. ശ്രീ N.S. Chandrasekhar worked on the system engineering side of and spacecraft integration, testing of Aryabhata, Bhaskara 1 and 2, Apple and IRS satellites. He is basically specialized in system engineering as well as EMI, EMC area. He has also worked in many other companies after retiring from ISRO. He has won Indian Invention Award in 1977 for the development of vertical dynamic balancing machine. He has been awarded a Distinguished Achievement Award also. There is a lot I can speak about Dr. Chandrasekhar, but because it's our LUCA and KSSP culture, I try to make it very brief. After retiring from ISRO, he has worked in many companies. 2 of them are Apollo Computing Laboratories and Greentex Communications Limited. I'm quite happy to introduce Chandrasekhar because there is a big generation gap between him and me. I joined ISRO quite late. Once ISRO is well established during Apple time, while Dr. Chandrasekhar was he did the spade work in preparing, testing, integrating all the aspects of Aryabhata satellite. So he is that way a big pioneer for us. And I am quite proud and I consider it a privilege that I am asked to introduce Mr. Chandrasekhar. Over to you, Mr. Chandrasekhar. I hereby invite Mr. Chandrasekhar to start his presentation and talk.
We were very young people from the colleges, just like a university campus. We treated the ISRO and the architects, 3 architects I want to mention. Even during my presentation also they will come. Is Vikram Sarabhai, Professor Satish Dhawan and Professor U.R. Rao. These are the 3 main architects of Indian space program, especially the spacecraft segment of it. Okay, good. So now we'll go through the presentation, or should we put a talk on how the technology events took place to initiate the project, and then how it got converted to a base for our foundation or for our future Indian space program. Aryabhata, now we initial stages, it is called as Indo-Soviet Satellite Project, because it was a collaboration between India and Soviet Union, wherein Soviet Union will support the Indian team, Indian Space System, with a supply of solar panels and onboard battery, which is a nickel cadmium battery, and also a tape recorder to store the experimental data which is being collected by the experiments when it is going around the Earth, and transmitted down to the Earth during the visible period of the satellite to Earth. So these are the few points which initially was discussed, and also Russians offered a free launch facility. The rocket was provided by them, and then we started in a very humble way. We took some ordinary industrial sheds. Professor Rao was the only person who had been an experimenter in the Voyager spacecraft, that is, studying the cosmos of the universe. So he only, except him, all others were freshers from the college. We started the project and then took initial few steps like any child falling down, getting up, walking like that. Then we started seeing some screen of the project taking shape. So as you have seen now, it is today we are on the eve of launch of Aryabhata, Golden Jubilee celebrations. So 50 years back, the amount of tensions and hiccups and joy of launching our own hand-built satellite, Aryabhata, was a great pleasure to us. To be frank with you, I wish to slightly give you some input on that. Till the Prime Minister Indira Gandhi announced that the satellite Aryabhata had been launched, which was at 5:30 p.m. in the evening, we all were locked up inside a place, inside a room in launch site in Kapustania, and also in India, in the Bangalore Indian Scientific Satellite Project. Okay. Next. The Aryabhata was the first Indian satellite launched in April 1975. As you are also aware, it is basically the mathematician, astronomer. This was an opportunity given to us by the friendship which we enjoyed with the Soviet Union in offering a free launch of the satellite Aryabhata, and also supporting us in the key elements of solar panels, which were very difficult to get at that time, which is a space qualified. That is radiation hardened. We will discuss it later. And secondly, a nickel cadmium battery, which is again space qualified. Then also additionally, to spin the satellite, they gave us titanium bottles with interconnections and pyro cartridges for spinning the satellite, where the cold gas is freed up. The key features of Aryabhata included: the satellite was primarily intended for the scientific and technological research in the areas of ionospheric studies, like though it is aeronomy they call, ionospheric. Then solar physics is basically on the neutron gamma ray radiation, which was initially planned. This was a experiment by Tata Institute of Fundamental Research, and X-ray astronomy was also by the physical research laboratories. The launch vehicle we used was a Cosmos 3M rocket. Experiments, as we had discussed here, the main significance was the launch of Aryabhata was a major milestone for our Indian space program, the foundation for the future satellite and space exploration and missions. A typical launch flight model of the Aryabhata satellite. Now, this is the key specifications of Aryabhata. The weight of the Aryabhata was 360 kgs. As you can see here, onboard power was only 46 watts. With that 46 watts, we had to build a satellite main control system, sensors, telemetry, telecommand, and experiment, supporting the 3 experiments, which is a Herculean task. How did we go about? We'll discuss it at a later stage. Then we used the communication system for uplink and downlink. That is for commanding the satellite and also collecting the data from the satellite in VHF band, basically 113.7.44 and 148.10. These are the 2 frequencies were used for downlink and uplink. And orbit was approximately 563 kilometers to 619. Perigee was 563 kilometers and apogee was 619 kilometers, which is almost a circular orbit. Okay. The inclination of the satellite is 50.7 degrees. So this resulted in a orbital period of the Aryabhata satellite of approximately 90 minutes. Okay. Mission life is expected was 6 months. Basically, it was extended up to 12 years. To which reasons we'll discuss later. The main objectives were to evolve a methodology of conducting a series of complex operations on the satellite in its orbital phase, to set up ground-based receiving, transmitting, and tracking systems, and to establish the infrastructure for fabrication of spacecraft systems. A typical configuration of the Aryabhata looked like a 26-sided polygon of approximately 1.4 meter diameter, and all faces are covered with solar panels except top and bottom. We had discussed on this inclination and others. Now we come to the architects of Indian space program. Initially, who were the main pillars in laying the foundation for the Aryabhata program. I cannot forget the father of Indian space program, Dr. Vikram Sarabhai, without whom we could not have stood with head and high under his leadership. But unfortunate and loss of him resulted in another pragmatic, very majestic, very dynamic, very result-oriented, the leader in this, Professor Satish Dhawan. In fact, I am proud to inform you all that I was one of the luckiest person to have interacted with him very closely during this program of Aryabhata. And the main architect of the Indian scientific satellite project and Aryabhata, its total execution program from concept to realization and launch in post, it goes to Professor Udupi Ramachandra Rao, U.R. Rao, a legend behind the India's first satellite Aryabhata, a visionary and a chief of ISRO also. In the younger days, how Professor U.R. Rao looked like. See, in the younger days, when he was a student and just when he went to US to join the experiment of Voyager, Professor Yorov looked in his photo like this. Now, making of Aryabhata, how Aryabhata conceived, how it was built, how it was resulted in a fruitful performance, building the infrastructure to the Indian space program. Let us discuss that whole program. In the making of Aryabhata, the development designed and built by Indian scientific satellite project. Initially it started with the Indian Indo-Soviet satellite project. It was renamed as Indian Scientific Satellite Project. And now it is named as Yorov Satellite Center in Bangalore. It was India's first entirely designed, built, and operated satellite. Hello? The next structure, it had basically solar panels mounted on the body to generate power, powered with solar cell and harnessing the solar energy, supporting the three experiments of X-ray astronomy, solar physics, and aeronomy experiments. Technology used was basically a spin stabilized. Why did we use a spin stabilized? Many people nowadays use a 3-axis. Say, now, why did we go for spin stabilization? Now, it is similar to a top we used to use in the school days. We used to tie a thread to that and then rotate, allow it to rotate on the floor so that it rotates exactly on its own axis. A similar principle is used here to stabilize the position of the satellite in the orbit. Otherwise, we will not be able to know whether it is looking towards sun or space or earth. So this was the first simplest method of stabilizing the satellite. Then we had onboard systems normally, which basically then includes power, telemetry, telecommand, attitude sensors, and experiments. Okay. Now let us go to the individual configuration of each subsystems or systems, which we call. A power system included a 24. See, Aryabhata had a 26 phases, which includes 24 phases plus one top, one bottom. So out of which 24 sides are covered with solar panels. So basically, why did we go for solar panels from Russia? Because they are space qualified. As you are aware, in the space, not only the temperature criteria is to 0 degree Kelvin. It is 0 degree Kelvin is minus 273 degrees centigrade. And also, when solar panel is exposed to sun, its temperature can go up to plus 100 degrees centigrade. Okay. And due to various X-rays, gamma rays, and other particles, lot of radiation will be impinging on the solar panel. So this all makes a solar panel to be ruggedized. Ruggedized in the sense it should be hardened to all these criteria. That's why we didn't have any facility, neither nor the technology to develop such a solar panel. Hence, Russians supported us during the first satellite, and later on we mastered the technology. Next, coming to the batteries. When we come to the batteries, we were using nickel-cadmium batteries. Why? The normal lead acid is a liquid, so we cannot use it. In this space, it is not allowed to use a liquid batteries because it bursts in a vacuum, it bloats up. Second, if you use a silver zinc battery, its lifetime is very less because depth of discharge, what we call as depth of discharge, is very high, up to 20%. It generates higher power but short life. Only nickel-cadmium batteries were the best qualified batteries for space exploration because it can live for longer period, say 8 years, 10 years, because it was allowing only a depth of discharge of 20%. The life of a battery is always dependent on the number of cycles of charge and discharge cycles, and also depth of discharge. These two were the criteria in selecting the battery. Now coming to the various other electronics, power electronics, we had a lot of power regulation, distribution, fail-safe operations, etc., which is part and supplying the power to the various subsystems or units. Now let us come to attitudes and spin stabilization. A spin stabilization was achieved by firing a cold gas jet system obtain a rotation of 90 revolutions per minute, which we'll discuss it later. And also sensors included a triaxial magnetometer. It is indigenously developed triaxial magnetometer. And I should congratulate Dr. T.K. Alex, who was heading that sensors group in developing this particular sensor, which basically is now a hot cake in Indian light combat aircraft program of Tejas, because it gives you an additional sensor for locating the aircraft position with respect to the Earth. What this triaxial accelerometer does is basically takes the Earth's magnetic field and generates in 3 axes the coupling, what are the voltages coupled. And by resolving the various equations, we will be able to achieve the local position of the satellite with respect to the Earth. This was one of the major achievements, I should say, thanks to Dr. T.K. Alex in this field. And additionally, a lot of the... So we had to manage it by a black body radiation to mirror or a white body emission. The complete spacecraft structure by black body and white paints, we could control the temperatures. This is a typical electrical black schematic of the satellite. We have power system, we have telemetry, 128 channel PCM telemetry system, a command system, tape recorder, the various sensors, then coming to the tracking units, and a hybrid coupler transmitting to the antenna or received from the antenna, and powering the 3 experiments, X-ray, neutron gamma, and ionospheric experiments. These are the panels, typical panels supplied by the... See, this is the making of Aryabhata. Now I'll describe the various electrical or electronic systems which made the Aryabhata space a complex system. In this, if you look at the solar arrays, it was a body-mounted solar panel of 24 in numbers out of 26 facets of a octahedron satellite. Top and bottom were not covered by the solar panels. Otherwise, the rest all are covered by solar panels, illuminating and generating a 46 watts under optimal solar illumination conditions. So this was the power available to the equipment inside the spacecraft. In this, they have to manage the power and distribution, telemetry, telecommand, sensors, transmitter, receiver, and 3 experiments of the neutron gamma, X-ray, and ionospheric. So it was a very tricky, complex problem. How did we solve this problem? We'll discuss it at a later stage. And it generated a spin-off in the... So next, let us come to batteries. See, batteries, as we see, batteries basically is a 3 types. One is lead acid. This is basically a liquid-based battery which cannot go in the space because of the vacuum conditions. Otherwise, there are silver zinc batteries, then the nickel cadmium batteries. Why did we go for nickel? Why we didn't go for silver zinc batteries? Because it has got a high energy output, no doubt about it. But because of higher depth of discharge, it was not able to support a long time operation of the spacecraft. Okay, it is a 80%. We call silver zinc has got a depth of discharge of 80%. Hence, it was not suitable for a long duration operations. Nickel cadmium basically is a 20% depth of discharge, and hence it was able to support for a long duration operation. The life of a battery is basically dependent on the charge and discharge cycles and the depth of discharge. These are the three conditions under which a battery's life is estimated. So we use, thanks to Russians again, it was a radiation order nickel cadmium batteries beautifully served our purposes for 12 years plus. Power conditioning basically was managing the distribution of power, regulation of power, and isolation of power from the outages. So this comprised of the power system. Next we come to the attitude and spin stabilization. The spin stabilization was achieved by firing a cold gas jet system using a pyro cartridges to spin the satellite up to 90 revolutions per minute. We'll discuss on this issue again. Now coming to the sensors. The sensors, what we developed here, first time from the scratch, it was developed a triaxial magnetometer and solar sensor to measure, to determine the satellite aspect, that is elevation and rotation with respect to the sun. That is basically elevation and azimuth of the sun. So this comprised the main takeaway of this development was the triaxial accelerometer, which was developed, was a very high accurate and very successful development developed by Dr. T.K. Alex, who is at the time he was heading the group, and it is being very successfully deployed in all our Indian fighter aircraft programs also successfully with little bit of adaptation. Okay, next we'll go to the next slide. This is a total electrical schematic of the satellite, where we talk of a power conditioner, regulators, instrumentation, telemetry, and telecommand systems. Each of them we'll discuss in later. And a tape recorder also is there, being transmitted to the space by antennas. There are 4 antennas transmitting to the space, giving a omnidirectional coverage while passing through the India. These are the 24 panels of 26 faces of the satellite. These are small details we can. This is basically to interface with the launch site when spacecraft is on the launch on the rocket. Till we launch, the battery should be charged, optimally charged. So we use a lot of schemes to ensure the normal operation, emergency operations, charge, trickle charge, discharge, etc. Battery conditioning. Here, this is basically when the satellite is spinning itself around the Earth, it's also rotating by itself on its own axis. So the various sensors which I talked of, sun aspect sensors, they generate pulses. They, using that, we have to divide the whole space at every rotation into 32 sectors. So using the 32 sectors, we will be able to identify which experiment is looking to the sun, which experiment is looking to the space, which experiment is looking towards the Earth. So this particular sensor gave a tool to locate, the image captured by these three experiments or results captured by three experiments and its locations. There is a typical scheme used for that. These are the sensors. What is now you are seeing is a sensor. This is a sensor of sun aspect. Basically, if you rotate it by 90 degrees, it becomes a rotational measurement. If you make it vertical, it measures the elevation position with respect to the sun. This is a triaxial magnetometer giving the X, Y, and Z information on the processing unit. Next, we will go to the telemetry and telecommand systems. This is a typical telemetry system wherein we have encoders. Basically, the encoders collect the data from various subsystems like power, sensors, experiments, attitude control sensors, and all this information. It could be in analog form, also it could be in digital form. All these data are formatted and then sent in real time to the subcarrier oscillator and then to the onboard transmitter to be received by the ground station. Additionally, they also have interfaces to tape recorder collecting the same data. On commanding from the ground, the tape recorders will come on and replay the data at a 10 times the speed. So this was the typical downlink telemetry system. This is an onboard telemetry system wherein we had a transmitter, a hybrid coupler, a one side, two receivers, and then a decoder going to the command decoders. The command decoders, there were 3 command decoders, and we were using majority voting logics. All the commands sent were 6 times we were used to send, and minimum we wanted it to be 4 times, it should be same. So majority voting logic was applied. Whichever is passing that logic, the command was decoded and transmitted to individual command control rings. Further, from there, it is to command the various subsystems, systems, and experiments to generate the further action. You can see the complexity of a typical experiment. How much of depth of technology has gone into building a experiment. A lot of, we had used the scintillation detectors. They are very high voltage detectors. Then we had to isolate that power from the others. So we used a isolation converter, that is DC-DC converters. And you can see here scintillation detector operates at 15.5 to 155 keV with a plastic scintillation. So this is the amount of power, voltage we used to apply. It is very dangerous. We used to really feel we are afraid of going nearer to that. Now let us come to a schematic of a various complex systems of Aryabhata. How Aryabhata totally assembled, how we were able to test it for complete functionality, interface, and then for performance evaluation, both in the laboratory in Bangalore and also before the launch, after reaching the very post-dispatch check and pre-launch operational checks. All the functions were done using 2 modes of testing called cable checkout and RF checkout. Moment we connect it to the cable, see some of the connections from the spacecraft are connected to the testing system using a cabling called as umbilical. Umbilical basically similar to a umbilical being naturally on every man. So till it separates during launch. That is one. Secondly, once the heat shield is covered, we will not be receiving any signal. So Russians came out with a solution of a retransmission probe. I'll give you some of the takeaways of technology which we have learned during the Russian interactions. This retransmission probe gave us an advantage of transmitting the received RF from the satellite even under the covered condition, connecting it to the telemetry data processing at the launch pad ground station and further processed using a PDP-11 computers. We had only PDP-11 computers those days. A typical setup of the checkout system you can see here. And this is a disassembled mode of Aryabhata satellite. The one in the extreme left you can see is a top hat of the Aryabhata satellite. The middle what you are seeing is the equipment bay, wherein all the subsystems are assembled, fitted, connected, made operational. How we are doing it, I'll explain later. The bottom shell, we used to call it as, was supported by this cold gas storage balls. We can call it as tanks, and piping done using inconel tubings and fired on two on vertical side, two on the horizontal side to generate a couple for rotation and also correction for the attitude. So this was a simplest method of attitude control. Same thing under testing mode. We are under testing mode. This is the ground station compatibility test. We had carried out the Aryabhata prototype. We could taken it to Shah, connected, lifted it through a helicopter, and tracked the satellite as the helicopter moved across to ensure proper functionality and compatibility with respect to the ground station. Next, coming to these are the things which are basically to be the learned and imbibed in our quality structures. What is the main takeaway for this particular program? We all we never knew what is happening, but we never knew what is the space electronic component, why it is so critical, why it should be reliable, what makes it reliable, how to ensure its reliability. All these things were a Greek and Latin to us. Thanks to the great legend, Professor Yuval Rao. He gave us like a primary school teacher, guided us step by step, step by step, step by step, and we realized that structure. See, how do we assure a quality? Basically, quality is assured by with some processes. What are the processes? Either you have to believe the manufacturer, or you have to evolve a process under which you ensure the infant mortality. The infant mortality just after any child is born, till it stabilizes in this world, we take care of so much, We ensure that it gets recognized, breathes properly, all the dusty atmosphere, heavy rains, temperatures, and all. Similarly, we should ensure that. So we evolved a process called thermal cycling. For you to use the space qualified components, we evolved the screening test to eliminate the infant mortality failures, thermal cycling test, burning test, vibration and shock testing, electrical parameter testing, and in this diurnal testing we used to call. Diurnal testing essentially calls for 1 week of burning. That comes to 168 hours of burning tests. Okay, this is necessary for any long life equipment. This should get into the culture of our system developing, building, manufacturing applications. Okay. Next comes to very typical to our space programs of radiation hardness assurance. Ensure components can tolerate the radiation exposures, total ionizing dose and single effects, and radiation hardened parts are shielding techniques if necessary. So this is called engineering. We'll talk further some of the questions we can answer on this subject. And the reliability analysis and redundancy. See, earlier it was those days I'm talking of, not today. Earlier those days we used to count the number of components. Higher the number of components, higher the failure rates. Lower the number of components, lower the failure rates. How to ensure the failure rates? By applying various redundancy, hot redundancy, cold redundancy. All these are the topics which can be deliberated at any other later date. Okay. The final QA review should be an independent QA team performs the audit and signs off before the launch. This is called as independent auditing and signing, which also ensures all components, subsystems, systems, and satellite must pass the flight readiness review. This should be a collective decision. No one-man decision should put the system into a great loss. This is a various culture which we imbibe in the Aryabhata days, and even today, I'm no doubt it is being followed in this way. Now, what was crucial? A tiny flaw in a space electronic component can lead to a major failures, which happened. We'll discuss at a later stage. QA ensures that what goes up stays reliable for years without any second chance. So, coming to this point, there are some few quality slogans which I want to make. Okay, shall I restart? Please say yes or no. I don't know whether all of you are listening to.
Sir, we all are listening your valuable session. Please go on.
Thank you. See, in a quality slogan, people say, a man makes no mistake. He is the one who never works. I hope you all will agree with me. Next, second statement is, any last minute changes are blessed with 100% failure rates. So don't make any last minute changes to any design. It should be, any change should be reviewed, pros and cons should be understood, and it should be tested, and then only evaluation for the change should be accorded to. This is one of the takeaways for the quality assurance. Okay. So, one thing there is next, we'll go to the next stage. A lot acceptance testing. See, here in our ISRO culture, we used to do 100% screening of the components initial days. Of late, it has changed. Maybe because the confidence level on the components and the manufacturing and the various criteria which have been set by the government standard have improved, and it has gone to a lot acceptance. The mechanical integrity checks, environmental stress checks, destructive physical checks, analysis. These are the three things being done. Last but not the least, traceability and documentation, which we as Indians very poor at it. We are very, very poor at it. Okay. The assembly and quality control. Follow a clean room protocols, ESD safety, precision soldering technique. At that time, we never had a machine assembly done, and soldering done, ray soldering or assembly soldering, PGA soldering, and all are manually done. So, lot of precision training and all were imparted to the technicians. And use optical inspection tools. It should be 100% inspection. No component, no joint, no process should not go to the next stage without inspection. Inspection, test, evaluation, and resolving the anomalies through various processes of, again, re-verification, revalidation, and retesting. So, and some of the X-ray inspection for the hidden solder joints like VGA. Functional testing, run the system level checks to ensure proper functioning under all operating systems, and also simulate all non-operating systems and ensure robustness of the systems. This is the second line is not written, but it should be done. Third, simulate the space environment like thermo vacuum chambers, vibration chambers, etc. The flight qualification is basically to ensure the system, integrate the various subsystems and satellite and do flight model testing, verify a performance under the launch and orbital conditions with minimal stress on the component. We call in the modern days as environmental stress screening. It is not that any other deep testing or a restrictive physical analysis, but it is a minimal environmental stress screening to ensure any manufacturing defects and also quality defects in the material selection. A historical launch photograph, Professor Dhawan, Professor Yoro, and all others here in Moscow. This is recently we had celebrated on 10th of March in 2025, which happens to be the birthday of Professor Yoro at the premises where we built the Aryabhata. That is, we call it as Electro-Optic Systems Laboratory. In that place, we have inaugurated a Yoro statue. The current chairman of ISRO, the former chairman of ISRO, all are in the photo here. This is a momentum being accorded by the chairman ISRO for all people, persons who work in Aryabhata project. I happen to be the one who is just now receiving this. You can see the young faces during the Aryabhata days. Some of them are the heads of the group. Some of them are presently no more with us. And background, you can see the Aryabhata. This is a typical spacecraft equipment under test, performance evaluation. Now, key technology benefits of Aryabhata, let's say. First step toward building a indigenous satellites proved that India could design, develop, and manage the complex space systems. Yes, we agree. Mastery of spacecraft systems. Yes, we have done successfully and we have taken it further. Experience in satellite fabrication. Yes, in this structure is presently being supported by Hindustan Aeronautics Limited. The key success of building capability in engineering manufacturing techniques, the key success came. See, none of the people individually power systems are manufactured by X. The communication is done by Y, telemetry is done by Z, and all of data handling by another person. All of them bring the equipment to the satellite. How to put them together? In what sequence we should put them together? How to ensure its interface? How to ensure the robustness of the previous systems? How to ensure the compatibility with the new system? How it is able to deteriorate or improve or match the required requirements? All this being is a function of system integration, comprising the system definition, the interface control, management of electromagnetic interference and compatibility, evolving a systematic approach to assembly, integration, and testing, including test plans and procedures, development of infrastructure, right from accepting the equipment till the launch. It is the responsibility of the integration team to ensure he is not the designer, But finally, he is the owner of the satellite. He should ensure everything is properly functioning till the end, till launch and post-launch. That is the duty of an integration engineer. This technology, this particular functionality has given a lot of leverage in building various complex systems in India, which we'll discuss at a later stage. Boosted the software and systems engineering, led to the development of onboard logics, ground control systems, and international collaboration, how to deal with the outside agencies. And it was a great foundation for future missions like Bhaskara, Apple, INSAT, Chandrayaan, Gaganyaan, Mangalyaan, and all. We are much more. We are going to see much more. The development of a ground control infrastructure necessitated the creation of a ground stations, control centers, building India's capability in mission control operation and satellite tracking. These are the key technology benefits which we are having. Takeaways of Aryabhata project. The available power was during the elimination was 46 watts. India was the first country to build a satellite with a CMOS technology, electronic chips. Till then, CMOS was never used in the spacecraft. We are the first people in the world to use the CMOS chips in the electronics. Built a technology base for spacecraft building, launching, and handling in the in-orbit operations. Declared the presence of India as a strong contender in the space exploration and utilization. Established a methodology of quality assurance, quality control, system integration, system definition, system control, assembly plan and procedures, development of equipment, facilities, infrastructure of complex systems and missions. These techniques were helpful in various other projects too. A big picture takeaway, Aryabhata was not just a satellite. It was India's classroom in space technology. It taught ISRO how to build, manage, and think like a spacefaring nation. Every Indian launched things then stands on the shoulders of Aryabhata. Tomorrow, you are going to see in our ninth golden jubilee of our successful launch of Aryabhata. In the planetarium in Bangalore, they have a celebration going on wherein the various eminent scientists and also the others will be delivering lectures. Those who happen to be in Bangalore and visitors visit the function. Thanks a lot for great patient hearing.
Thanks, Dr. Chandrasekhar.
Yes, sir.
If our participants have any doubts, we can have a answer session. We are already crossed the 1 hour. So let us make it as quick as possible.
No, I have no issues, sir. This is my favorite topic. If they, as long as they're satisfied, I'm happy. Okay. Shar is Sriharikota. It is a place near to Chennai, wherein we have established in India's all a launch port. We can say this space station, space launch port, wherein we'll be putting our spacecraft on the rockets there, and also we were using in the earlier days as a ground station for receiving the satellite data. Next question.
Sir, from this Aryabhata, what were the satellite data transmitted to the Earth? Means the telemetry data. Means like temperature, battery voltage, or
So it
something like
started
that.
from everything, sir. It started from the, let us start from power. In a power, what was the solar array voltage? If when there is no solar array, what is the voltage? Then what are the onboard systems? In a very onboard load, you call it as a load, like a telemetry, telecommand, instrumentation, let us say sensors, attitude control, then the tape recorder, then the telecommand transmit receivers, telemetry transmitters, all experiments 1, experiments 2, experiment 3, all of them are individual systems. So each one of them, how they are operating, whether they are operating normally, abnormally, whether they are functioning properly as far as the power goes. And what is the battery power left? What is battery? Is that fully charged or not charged? It is under charge or such conditions. Next is we also, apart from that, we had with the onboard transmitter and receiver. We are supposed to monitor the satellite distance in orbit at every time. So we had called a range measurement and a range weight measurement. A range measurement, basically, we used to send the various tones like 4 kilohertz, 40 kilohertz, 400 kilohertz, and all. We know what is the speed at which the light velocity goes or the microwave reaches. And we used to receive back and calculate what is the time taken, and accordingly we used to estimate the distance between us and the satellite in real time. That was one. Secondly, at what angle satellite, when it's coming, is with respect to the local station, like it's a Sriharikota. Sriharikota is located in somewhere around, say, 20 degrees in elevation, around 70 degrees in the azimuth. So, under that condition, when how the satellite enters, we allow the entry of the satellite to the exit of satellite. So we used to monitor, and angle we used to measure also, like what's called the interferometry. The interferometry basically defines two antennas located on the ground with a known three, let us say, not two, three antennas, which are separated by distance, known distance, and a known angle. So that satellite data, when it is receiving, each one of them, when it is received, they measure the time between them, the time entry between them. So they used to measure the angle. So the reverse of it is now what you see in GPS. Now satellites are fixed on the space. You know, it's ephemerics. We call it as ephemerics. Is the satellite's position at instantaneously, and based on that data, we know where we are. So that time we used to measure the satellite position. Now we are measuring the person's position with respect to the satellite data. Okay. Next comes
Thanks
to
for your very good reply, sir. You explained more, and when you said about the three antenna, same picture came to my mind about the GPS. Okay, thank you once again, sir.
Thank you, sir. Thank you. Next, please.
Monica has some question, I think.
Good evening, sir. Sir, if Dr. V. Narayanan, who is the current chairman, if he had participated in this satellite program, then what was his role in making Aryabhata satellites? Sir? Could you please explain that?
Okay, shall I come to you? I am a 4 years old man. Okay, so V. Narayanan is still young, and he joined ISRO in 1994, wherein we had launched the Aryabhata in 1975. And if he were to join, he is a propulsion man. He's a rocket science and rocket propulsion man. What is a rocket science, rocket propulsion, and all we can discuss on another lecture program. Okay, he's basically a propulsion man who has extensive knowledge and exposure on the cryogenic rocket engines, which is of the current requirement, and his knowledge and exposure is very useful to the country. And I hope he will take the ISRO to a glory in his days to come.
Thank you, sir.
Sir, it is really amazing to listen that with the 40 watts we manage one satellite. So nowadays, sir, how much is the power generated by the solar panels? Say, for example, this Chandrayaan and all, how much is the consumption?
We take the Chandrayaan and all. Basically, it is dependent on the mission. It's a mission-based solar panels are used. They are using a 3-axis body stabilizer. That means satellite is no longer rotating on its own axis. It is kept in a position either looking towards the Earth or looking towards the Sun or looking towards the Moon or Mars. So they are 3-axis body stabilized satellites. And only the solar panels are always directed towards the Sun. So because of that and the number of panels and the efficiency which we use, we are able to generate up to 3 to 4 kilowatts of power.
Mithul Francis had raised a question, which was the best satellite of India.
Under what conditions? See, best conditions are basically utility point of view or thrill point of view or exploratory point of view or just for celebrations. So these are the various criteria we have to set, From the utility point of view, till today, if you ask me, the INSAT is the best program which the India has ever built and well utilized. Okay. Next comes is the technology development goes various technology complexities, various technology development, etc. The moon landing, I feel, is another great success, and also the Mars mission. But to be frank with you, another beautiful satellite which we are missing is the remote sensing satellites. I'll give a small introduction to this remote sensing satellite. Hitherto, till India came into the remote sensing satellite, the other countries like America and Europe or Russia were using the technology which was one grade inferior to for mapping the Earth masses. Earth mass means land mass, sea, etc., etc. They were using a technology called as basically a scintillation detector. Do you remember earlier I had expressed you on the X-ray experiment? So it was a high voltage and it was likely to be a point of concern for success. So with a bold decision of Professor Yuval and Professor Dhawan, I can say, we entered into linear image self-scanning system, which is basically a charge-coupled array device. This changed the scenario of the whole world in doing a remote sensing operations. We were the first people very successfully doing in IRS a 73 meter to a 36 meter in the first satellite. Later on, today we are even come below a meter in Earth resources mapping. And with the RIASat is another radar imaging satellite which measures the ocean temperature. The ocean temperature will give the meteorologists, the meteorologists to map the various hurricanes, tornadoes, tsunamis, etc. And also predict the rains, bearing clouds and other, etc. Last but not the least, the food fisheries for the fishermen where they can get a better yield. So with all these advantages they gain, so nowadays I still feel India is a leader in the Earth observing satellite, remote sensing and Earth observing satellite. And Gaganyaan is basically a good exercise. We used to look at what are the takeaways from this after the launch, but very good objectives are kept. We hope it will be successful.
Should I express my vote of thanks to Mr. Chandrasekhar? Mr. Chandrasekhar, it was a wonderful talk. You went quite deep, and probably many people who are interested in satellite technology, that will be rewarding, because popular science talks generally cover very superficially, talking about rockets, satellites, and other things. But at a time when Even the electronic devices were DIP chips. You people made Aryabhata a legend. Thank you. Thank you very much for the talk.